Okay, so the last video we recorded I deleted because I did not number the video correctly. So we're on video 89. We're gonna pretend the last thing I streamed just does not exist. What we're doing is proving that someone stole your code by encoding a special phrase into the code that can't be found in a hex editor. So let's demonstrate that really quick to prove that that's actually what I'm doing and that I'm not like full of crap here. So so this thing here, I need to finish this for a second. So right. Okay. So let's say that we have, well, actually, let's just do this. So if we take, so I have a build script for this. So sp2.sh, it looks like a lot of stuff, but it's really not a lot of stuff. It's just compiling this, and I have very specific arguments that I like to use, but you can just, if you know how to compile a C file, you just have to compile this code. You don't have to do anything fancy. It's just I have some very strict options for how I compile. Anyways, so let's do /sp2.exe now that we've made it, and we're going to supply it an argument called purple penguin, or no, how about blue barrel? Blue barrel. How about that? Blue barrel. Okay. And then what we're going to do is we're going to take this hex code here that we have, copy it, and we're going to paste it into this statement over here. Right? We're just going to paste it right here. And it's 4 pixels worth of data. So we're going to make this a 4 here. And then we're going to recompile. /sp2.sh. Okay, clear, and then we're going to run it. .sp2.sh, and then blah, 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 blah. And we can see that it says blue barrel right here. So right here it says blue barrel, right? And where is blue barrel? Like if we go take this and we go Control F, and we look for blue barrel in the source code, it's not there anymore. Okay, now if we take the executable, let's take the executable, go File, Open, and open up sp2.exe for a second. If we look for the Twitch URL, we can't find that. That was from an earlier tutorial. Let's look for AAC 2020. So AAC 2020. So we see kanji coder AAC 2020 right here. And that is from this string that is embedded into the source right here. Okay, but if we look for blue barrel, we can't find it in the hex editor, right? So it's just not in there because it has been encoded into here, right? So if we want to hide a message in your source code to kind of prove that somebody is using your source code, then this would be a good way to do it, because if you want to make it so, you have like a sequence, this could count as like a signature, right? A signature to prove that the source code is yours. So if somebody else compiles with your library, is using your engine, and they're compiling a game with it, and let's say they're not paying you a licensing fee or whatever, like for instance, I want to do something where if you make under $100,000, you don't owe me anything, and then after every sale after 100,000, there's like a royalty. So if I want to make sure that if somebody tries to sneak by me and say they're not using my engine, but I look at their game and it looks obvious to me that they're using my engine just because of the style, and my engine has a very specific style to it, I can inspect their executable and find, you know, this kind of signature in the source. And this signature, if you hide it correctly, nobody's going to realize that, oh, this is actually a signature that proves that it's my library, right? And if you have a lot of library code, then you can hide something like that in an unobvious place and nobody knows what to look for, right? Because you don't know what that signature is going to spell out, right? So they don't know what string to search for. And even if I know to search for blue barrel, well, searching for blue barrel doesn't get me to here, even though this is where blue barrel is encoded into the code, right? So the next thing we want to do is, in this terminal, we want to encode, what we really want to encode is this, right? We want to encode the address to our engine. Okay, so let's try that right now. So clear ./sp2.sh, and then we're going to paste as an argument the URL to our source code. And what did we do here? What went wrong here? Oh, my bad. That was the sh file. We wanted to use the exe. ./sp2.exe. We're going to paste this thing that we want to encode, and then we get the code for it, right? So we got this code for it, and if we want to confirm that that code is correct, we can now hard code it into our executable. And let's clean this up a bit. So before we print this off, let's just print a new line, because printf \n, and then let's print some other lines right after we print this. So let's like do this here. Just so it's a little bit easier to see what's going on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So we got 11, so let's put 11 there. Let's clear ./sp2.sh, so we're going to compile it again. And then we're going to clear ./sp2.exe, and we don't care what the input is this time, so just blah, 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 blah. And now we see github.com/kanjicoder AAC 2020, right? So now that we have this, let's just get rid of this demo string, right? Let's get rid of this demo string for a second to prove that we're actually encoding this and that it's actually the secret message that you can't even find if you use a hex editor, right? So clear, git status. Actually, that's not what I meant to do. It's just a habit, sorry. ./sp2.sh, so we're going to compile with our build script. Then we're going to clear ./sp2.exe, whatever, we don't care what the next argument is. So this is the code, this right here is the code for whatever, and this is hard-coded, right? So if we take this string and we try to find it in the source code we're writing, it's nowhere. We can't find it anywhere, because it is encoded right here. And if we go into the hex editor, so let's open it up again. So file, open, we're going to reopen the executable. If we look for AAC 2020, we shouldn't be able to see it anymore. Yep, can't find AAC 2020. Remember, we could find it earlier when it's hard-coded as a string, but now it's hard-coded into the bytes. And because it's hard-coded into those bytes, we cannot find it anywhere. And we might be able to find it if we search for this here, and we search for like little endian, big endian. We might be able to find it, but we won't be able to. So let's do hex values. And there should be little endian, big endian, shouldn't there? Well, let's just try it. Can't find it. Now, that could be because the endianness is different. Like, I'm pretty sure it's in here, but, forward, backwards, integer number. Oh, here we go. So let's look for a 32-bit, and let's look for a little endian. And let's try that. Can't find that either. Okay, let's try big endian. Does this need to be like a 0x? Oh, hex values. I don't know why. Can we do this? Can we do that? There we go, found it. Okay, cool. So let's go move this over here. See if we can move this over here for a second. So let's see. Can we close this? We don't need this. Okay, so 68747470. 68747470. So you see how it's kind of backwards because This is looking at it in one order. These are the individual bytes, right? This is the endingness. That's why it's kind of inverted. So 68747470, 687474 and 70. Okay, well then where's this? 73 and the 2F. 1, 2, 3, 4. 7, 3. 7, 3, 3A, 2F, 2F. Yeah, so there's that, and then it's separated. What is it separated by? So I don't know how they encode, how this information is getting encoded, but, okay, well, let's see if we can find the next one. So, 67967468, right? We gotta read it backwards. So 67 69 74 68. So it's in there. It's in there, right? So if we look at this next line, 7562 2E63. 7562 2E, right? So here's the 2E. Then 63. Okay, how about this next one? So 6F 60 2F 4B. 6F 60 2F 4B, right? So it's in there. It's in the hex. It's encoded. But it's really hard to find it because, right, even though I know what I'm looking for, I can't find this exactly because there seems to be some type of byte sequence that separates each of these entries. So I don't know exactly how that's compiled. Like, that might be like an opcode. Like, so if we look at, so let's actually look at that. So this 4B here, 4B 2F, 4B 2F 60 6F, and then we have this 45E0. So we're looking for the 7.5. 7562 2E63. So it looks like these guys. This is 6F. Okay, yeah, so whatever these characters are, this might be some type of opcode. So, let's try to search this and see if we can find an opcode or something that this stands for. I don't know if we're going to have any luck, but let's look for opcode. Let's see if we can find an opcode for this. X86, it'd be a X64 opcode. X64 opcodes. So X64 instruction set. Let's look for that. Let's kind of see if we can find. I don't think the opcode would be 3 bytes is kind of weird for any type of instruction code, so I don't know. This isn't my kind of thing. Yeah, this is just going to be a pain. Okay, well, if this is some type of meaningful opcode, we should be able to find... let's try these two. Yeah, so I'm not really an assembly kind of person here, so I don't know what I should be looking for. But you get the idea. You get the idea that by encoding the data into your executable like this, it makes it pretty hard to to find, right? So let's rerun this, make sure that it's ./sp2.sh. Let's recompile this, make sure it still works. And let's do one more thing. Let's make it so that we can add spaces. Right? So this is hard-coded into here, but how can we make it so that we have spaces, right? We have more than one argument, right? Right now, if we do ./sp2.exe and we do 1, 2, 3, it's going to complain because we must supply exactly one argument. That's the way we coded it. So how could we write this code so that it will keep on going word by word and kind of like encode like multiple lines of text. Now, that's actually kind of difficult. So, I mean, it's not something I really want to think about. I really just wanted to get enough code to where I can make a little utility that would encode one word for me. So I think I'm going to keep it like this, right? Because I can do ./sp2.exe, and I can do my secret code whatever thingy, right? Right, and then I can have the thing to embed, right? So I just want some little thing that will let me know what the code is, and yeah, right? And then we have this little thing hard-coded here. So I actually like it like this. It's kind of ugly, but it's good enough. Let's... When we're printing this off, though, let's go into that loop here and just say... let's print off both of these. Can we print off both of these? So let's... if we wanted to print off both of these, how would we do this? Because right now, the way we're printing off this hex code stuff, we're really hackish here, right? We're kind of like taking this and we're packing it into there, but then we're printing it off right here like this. So it would be nice if we make like a printing function for this. So what we would do here is we'd do like sp2 print hex array, and we'll do sp2 pix 001, and we're going to print up to pi -1, right? And so we'll make a note. This is the big endian. And we're still being kind of hacky about it, right? Because we're just kind of like hard coding that, but that's fine. Little endian. Right? And then this code here, we're just going to comment it out. And we're going to say print hex array, right? So we want a function called print hex array. So we're going to make another section for this. And how did we decide we wanted to do this? Did we just say, does it take a limit how did we do this? Where are we? We're kind of lost here. We got way too much code here. So down here, print hex array, and we're going to take the array of pixels, and then we're going to take the, this is going to be the maximum index that we're going to print up to, right? So that's fine. So we'll just call it like SP2 pixels. So void sp2 print hex array, and then a u08, or actually no, a u32 pointer called sp2 pix array. Actually no, let's not namespace it if it's a parameter. So let's just call it pix array, and int32 maximum index, and for int pi equals 0, pi is less than or equal to the maximum index, and then pi plus plus, and then u32 var equals this pixel array with the pixel index, and then we have this logic already to print it off, right? So let's take this. Alright, so we'll print off 0x, and then we'll print off the hex, and then we'll print a new line and a comma character. Alright, and that's all we'll need. We'll also have to define the types we're using. So we're using a signed and unsigned integer here. So define i32 and define u32. Then in the bottom, we'll undefine these from this section here. So undef u32, undef i32. Okay, cool. So is this correct? Did we name this correctly? Yeah, so print hex array. So let's give that a shot. And why were we reorganizing this anyways? There was a reason, was there not? Oh yeah, because we want to polish this up a little bit. Like, I don't want to get to having multiple parameters just because I'm kind of tired of this, and it does most of what I want to do anyways. But I'll put this up on GitHub so that if you want to take a look at this to see how it works, you can do that. So I'm gonna get rid of this to do. And we're going to see if everything works. So /sp2.sh. So we're going to compile and see if we made any mistakes. So u32 variable needs to be declared. So u32 var, right? So we got to declare the variables we're using here. And I think that's the only thing I'm missing. Printf big endian %d, so we kind of cut and pasted, kind of wild and crazy, and weren't really paying attention when we did it. So the big endian and the little endian, right? Okay. Okay. /sp2.sh, and we're going to do, or .exe, and we're going to do our Twitch URL. So Twitch URL. I'm gonna try that out, and well, actually, well, that's not what I want to do. I want to do my git AAC URL. I wanted to use my GitHub, so let's use our GitHub here. So let's take this and delete it and paste that. Oh geez, what the heck. So I think I had an enter character in there, and that's why that happened. Let's just look at our GitHub here for a second. So let's just take this, copy that, go over to our terminal, /sp2.exe, right-click, paste, hit enter. Okay, cool. So now we have our big endian and little endian versions of the same code, right? So let's take this and copy it. Let's go over to where we're hard coding stuff, and let's make some room. And this is the little endian is the thing that we're successfully printing. So we're just going to call this big endian. And then we're going to make another one called little endian. So big endian and lit endian. And we're going to take big endian, we're going to shove it in there. So paste that guy in there. And then paste this one in the little endian section. And we're going to print off both of them. And one of them is going to be all garbled, but depending on what operating system you're going to choose, one will give the proper message and one will give the improper message. So are they still 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, so they're still 11. So then down where we're printing stuff off, we're going to say big endian. And then we're just going to do this one more time, and we're going to do little endian. Okay, so let's, now that we have that encoded, let's do cp2.sh to compile, or /, did I screw this up? Oh, sp2.sh, my bad. Okay, clear, /sp2.sh, whatever, I don't care. And now we see one thing is completely garbled, right? The HTTP is backwards here. This is HTTPS. I'm actually kind of like confused here. Oh yeah, the S from the HTTPS is over here, right? Because it's, right, everything is completely messed up. So every 4 characters is inverted. HTTP, so the next 4 is S://. Then GIT, get, H for hub, so hub.com/K for kanji code, right? It's like really hard to look at, right? But you see, this is our big endian encoding, and this is our little endian encoding, right? So now that we have this, why does it say must, hold on. /sp2.exe, whatever. Big endian, little endian. Okay, cool. And then it says what the text string is. So that's pretty awesome. We might want a little space between where we're printing off big endian and little endian. So it says big endian. That's weird, because we're kind of big endian and little endian. There should be space between here. Don't we have this space? Like, what's up with that? So I don't know why that doesn't look quite right. Oh, wait. My bad. This big endian, this is for printing off these guys right here. If we're looking at this, though, if we want to fix that up a bit, then we need to go and look at this. And we just want, like, a space before each one of these, and then a space after it, maybe. That might be nice. So we'll do, like, a printf \n right after this. Then we'll... Hold on. Yeah, an extra space would be good there. An extra space here would be good. And an extra space here would be good. And then just delete this crap here. Okay. Okay, that looks good. So, clear git status. Oh, sorry, force of habit. ./sp2.sh compile. Clear. ./sp2.exe. I don't care. So we got the big endian version of this crap I just typed. We got the little endian version of the stuff I just typed, and then we have what I originally typed, right? And then we have this little thing that's hard-coded using this code here, right? So that's pretty cool. I'm good with that. So I think I've made like the little utility that I want to make. And let's put this into a Git repo here. So let's take everything we've written and just kind of cut and paste it, right? Because we're working in our shortcut files here. So let's just take sp2.c11, sp2.exe, sp2.sh. Let's take all of that, copy it, and just paste it somewhere, right? So let's just make a new repo really quick, right? So, okay, so where do we want to put this? So in our drive, our repo drive, we got a Git folder. Let's make a kanji coder folder, because these are going to be a lot of little things. New folder, kanji coder. And new folder, what do we want to call it? We just want to call it, do we want to name it something fancy, like pixel signature? Let's call it pixsig for pixel signature. Let's paste this in here, and let's do a little bit more cleanup, right? Let's delete this, and let's kind of rename everything. So let's rename this to, Pixasig. Let's call it Pixsig. Yeah, let's call it Pixsig for pixel signature. And we'll rename this to pixsig.sh. And then within the build script, if we go into Notepad++, we're going to change sp2 to pixsig, right? Because we're going to rename the files here. Let's close all of these things here. In the C11 file, right, anywhere we see the sp2 namespace, we're going to change that namespace to pixsig. Replace, 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 replace. So anywhere we're finding sp2, we're just going to be like pixsig. So some of the formatting might be off, so let's see if we have violated our column limit in any aspects here. So, yeah, so right here, we might have to do a little bit of cleanup, right, like this is like, this is outside of our bounds. If we want to fix this, there's a few ways we could do it, right? Define pack. I'm gonna just do this. Alright, so I'm just going to create shorthand words for these. So pack number, pack this, pack that. So pack number 1, pack number 2. And then at the end of this section, we're packing the pixels. I'm going to undefine these like macros I made. Okay. And now that we have these, we still have a little problem. We have this print hex, right? So let's do define I'm going to say print H for print hex. And then wherever we see this, we're just going to say print H and print H. And then we'll undef it over here, right? So undef print H for print hex. And is there anywhere else where I'm going over my column limit because I've made everything longer? It looks like no. It looks like everything else is within our column limit, so I'm fine with it written like as that. So let's do a git bash here and open up a terminal so that we can check out this code, make sure that it is compiling /pixsig.sh, right? So that's our build script. It looks like the build script is working. /sp, or not sp anymore, pixsig.exe / whatever the heck, blah, blah, blah. No such file. Oh, so it looks like we have not quite changed the build script all the way. So let's look at this build script and see what we have in here. So we said base name, no extension. So, I don't know why this is hard-coded here, right? The base name has... Yeah, that's not quite right. Oh well, so we have... Our build script needs some maintenance here. Base name, no extension, but then everything here is... that's not quite how we want to do it. But... because I just want to keep this script dead simple, let's just do this. This is kind of ugly, but let's just... yeah, let's just keep it like this. Yeah, this is ugly, but let's just get it running, right? Let's just get it working correctly and not worry too much that the build script is crap. /pixsig.sh. So we're going to build it. And there we got a pixsig.exe. Let's delete this one. Okay, so now let's run this. So clear ./pixsig.exe and supply some random argument. And there we go. We got the big endian version of it, the little endian version of it, what we actually typed. And then we have this hard-coded thing of mine, the little endian and the big endian version of what I hard-coded into the source code. So that looks pretty good to me. Let's do a git status, git init dot, okay, clear, git commit dash am, first, see video, so if you want to know where, if you want to see like where we wrote this code, you can see it there. Oh, sorry, git add dot. And then let's try to do the same commit thing again. Okay, cool. And we will take this and we'll go out to GitHub and we'll kind of push this up so that you can take a look at it. So www.github.com. This is not my... I'm gonna sign out of this one. I'm gonna put this on another screen in case I accidentally show my password. So I'm gonna put it on another screen and sign in here. And okay, so we're gonna create a new thing, and we'll call it Pixig, right? Because that's what we named it. It's gonna be public, and description is going to be see archived video. And we're on video 8.9, right? 8.9? 8.9. Encode secret message into your source code to prevent theft. Right, so the idea is that, the idea of this repo is, see archive video vid IID 0089, encode secret message into your source code to prevent theft. I mean, that's basically what we're doing. Public, and let's just create that, right? So let's create it. And now that we have this, we'll take this URL here. We'll go over here, we'll do git remote add. We'll call it GitHub. Paste the remote. Git push GitHub master. And then it's going to be up there for everyone to look at. Oh, my bad. Denied because I am HeavyMetalCookies. And so the hackish way I get around this is I go into projects, or not projects, I go into settings. I'm going to have to send myself an invite. Manage access, and we're going to invite ourselves. Invite a collaborator. We're going to invite HeavyMetalCookies. There we go, invite myself. And then we gotta go to our Gmail, so I gotta move this up just in case you see what's going on here. Okay, I'm gonna accept that invite, and then we'll be ready to push it up. We won't get rejected once I accept the invite. So yeah, so now in my email, I see that, Kanji Coder has invited me to do this thing. So we're going to view the invitation, we're going to accept it. That doesn't look quite right. Oh, you know what it is? So the thing is with this kind of email here, if you are logged into the wrong account, the link in your Gmail just does not work correctly, so we have to sign back in to the HeavyMetalCookie account for this to work. So it's really stupid, but GitHub is only expecting you to have one account, so it kind of wrecks the workflow when you have more than one account. So okay, so now that we are logged into HeavyMetalCookies, now if we hit View Invitation, this is actually going to work properly. So there we go, accept the invitation. Bam, we accepted the invitation. Let's close this browser. And now if we hit up on the keyboard and we try this again, it should be accepted. Alright, awesome. So there you go. So if you want to see that, you'll have to go to my GitHub, but it's there now for you to use to your heart's content. So I'm going to close this, and I'm going to close this code. Actually, you know what? Let's close the hex editor. Actually, let's reopen that for a second. Let's open up. Let's go back to the repo drive and go to our kanji coder thing for a second. And let's, before we get out of here, because I know that initially when I started this project, I had stopped the video because I had the wrong number. And so I didn't explain everything that was going on. So let's take some time to explain exactly what's going on here. And explain like just everything in order so that you know exactly how this works. So print hex array. We have an array of pixels, right? U32s, and it's a pointer, so therefore it's an array. And the maximum index, right? So we're going to go through every single pixel up until the maximum index, and we're going to get the current U32 from that array, and then we're going to printf as a hex value. So we're going to append 0x because printf in C doesn't append a 0x to it, and we want a 0x, so we'll append a 0x, and then we'll use this to print off this U32 variable as hex with 8 digits, right? 8 digits because each byte is represented by 2 hex digits, and there's 4 bytes total with 2 hex digits each, so that's 8 character slots to represent a uint32 variable as a hexadecimal code. Okay, then after we print it off, we'll just do like a new line character. Okay, so next thing, what's here? So text to pixels. I don't know if this section is accurately named because we got a lot of stuff going on in this section. We have 2 buffers that are file scope variables. This one is for our big endian ordering, and this is for our little endian ordering, right? So we're going to do 2 encodings of the secret message, one using big endian encoding and the other one using little endian encoding. And the little endian encoding one will be the one that will print off properly when on Windows. And if you're on Linux, then you want the big endian. So big endian for Linux, and then for Windows, you want little endian to see the message properly. So pixig get byte. So we're going to take a array of bytes in a text string. This is the byte index, and this is the max byte index. And all get byte is a wrapper for index accessing an array that does some bounds checking. And if we're out of bounds, then we just return a 0 rather than go out of bounds and have a seg fault, right? So this is just a little wrapper function that is going to protect us from seg faulting, which is going to make it easier to encode values that are not a multiple of 4 characters. Okay, so pixig pack pixel 001. So this is our big endian network byte order version of packing pixel. So there's going to be 2 pack pixel functions, 1 and 2. One is the big endian, and this is the little endian. So with the big endian version, you see that the index, you start at the red component. So this index, this component index, is the index of the red byte. So you take the pixel index and you multiply by 4 to get the index of the red byte. And then you offset by 0, 1, 2, or 3 to get the red, green, blue, or alpha bytes respectively. And then you need to bit shift them into position correctly to pack them all into a unsigned 32-bit integer, right? So the bitwise OR is used to smash all of these values together, but before you smash them all together, you need to shift them into the correct positions, right? So the alpha is at the very end in the least significant bit position, so there's no shifting. This is 1 byte over, so you shift it by 8 bits. This is 2 bytes over, so you shift it over by 2 bytes, which is 2 times 8, 16. This is 3 bytes over, so it's 3 times 8, 24. Okay. And then we just return it here. Okay, so for this next pixel function. It's exactly the same code. The only difference is these numbers here are different, right? So we're going to pack the bytes in the inverse order. So we're going to go 3, 2, 1, 0 rather than 0, 1, 2, 3, right? Now you might notice that this txt and this dex might be confusing you if you're not familiar with C code. This is just a shorthand variable for these variables here. So this and this are exactly the same thing. This and this are exactly the same thing. And I just did that so that I could reduce the amount of column space I was using so that I wouldn't go over my right edge over here. Okay, so let's go down to the next function. Let's explain it all. Once we have it all explained, then we will get out of here. Pixel signal sig text to pixels. So we're going to take the text string and we're going to convert it to pixels. So here's the input text string, which is just a char array. Remember that a char array is just numbers, right? So we don't have any, if you look through all of this code, you're not going to see any ASCII to integer conversion anywhere because ASCII is already integer values, so we don't need to do any ASCII to int or int to ASCII conversions when we're in C because it's already represented that way. Okay, so declare our variables. Here's our pixel variable, our pixel index, our maximum pixel index, our maximum byte index. We're going to erase the previous buffer in case we ever decide to use this code somewhere else where we're calling these functions multiple times. This is kind of pointless in the executable that we have created, but we're just going to keep it here anyways. Better safe than sorry. Figure out the number of pixels. So originally the number of bytes was rounded down to avoid seg faulting by accessing bytes that don't exist, and everything had to be divisible by 4. That is no longer true, so let's make a note here. So at vid iid 0089, and the time is 51, 52, and 5 seconds. No longer true because we have a helper function, right, this thing, that protects us from out of bounds array access. Right, so that's no longer true. So the string length, we're going to do strlen of the string, and the number of pixels is going to be the string length divided by 4, right? Because we can fit 4 characters into each pixel, right? Because we have A, R, G, and B bytes. And we're going to do 1 byte equals 1 character, right? So each pixel has an A, R, G, and B. That's 4 bytes, and we can pack 4 bytes into a single pixel. So the number of pixels is the string length divided by 4. And remember, this is going to round down. Division rounds down in C code. So if the number of pixels times 4 is less than the string length, we know that we have rounded down. And if we have rounded down, we're going to add 1 so that we can make sure that we get the entire input. And if we do this, we could possibly go out of bounds of the array, but because we have this safety function here, if we go out of bounds, we just return 0, so we'll be safe. Okay, so then if the number of pixels is greater than our file scoped buffer, we're going to have to truncate whatever input we put into the executable. Or if our command line argument exceeds what the internal buffer is, the hard-coded internal buffer, then we have to truncate that command line argument. So we'll truncate it like this by saying the number of pixels equals this maxpix argument. Okay, so figure out the maximum byte index. So the maximum byte index equals the maximum number of pixels times 4, right, because 4 bytes per pixel, and then minus 1 because this is the maximum index, not the length. If the maximum byte index is greater than the string length minus 1, then we're going to have to truncate that as well because we don't want this bit index to tell us to go outside of the bounds of the string, right? So we'll truncate that. Okay, so what's next? Pack the pixel. So here's kind of the core of what we're doing, right? So we've been going from very granular low level to the more broad scope, right? We're kind of going, so the way you're reading this code is kind of inverted from how you're probably used to it. You're probably used to going high level and then drilling down, but we went from low level and we're going upward to more and more abstract levels. Okay, so we have some defines here just to shorten these function names. So this is our big endian pixel packing. Here's our little endian pixel packing. And here's our code to print a hexadecimal array. Okay, so we're going to say the max pixel index is the number of pixels, -1. And we're going to loop through every single pixel. And we're going to pack pixel per pixel. So this U32 variable is a pixel, and we're going to pack that pixel by taking the text string, the pixel index, and the maximum byte index, and we're going to use all of that information to pack 1 pixel's worth of data into here, starting at this pixel index, right? And we already looked at this function earlier, but we might want to look at it again for a little refresher here. So let's look at that one more time to see how that works. So pack pixel, right? So here's our string of text. Here's the pixel index. Here's the maximum byte index. So, right, we take the pixel index times 4, get the component index, and then we do all this bit shifting stuff. So this should look familiar, but I just wanted to review it really quick. Okay, so we do this to get the current pixel that corresponds to the first 4 bytes of the text string, and then once we have that packed, we're going to shove it into our pixel array, our big endian pixel array. Then right here we're going to do the same exact thing, but it's for the little endian pixel array. So our packing function for little endian, same exact parameters as the other function, but packing it into this array instead of this array, right? So it's the same exact thing. Like this is exactly the same as this, but this is the big endian version and this is the little endian version. Okay, so after we have that, we just want to print them off. So here's the big endian and the little endian. So we label them first. Then we use our print hex function to print the pixel array up to the last pixel index. The last pixel index is the last valid value in this loop. So after we exit this loop, this value is out of bounds by 1, so we have to subtract 1. So that's why we have this subtraction of 1. And when we print off this this code here, we may or may not have any null terminations. So to make absolutely sure we have null terminators, we're just going to print off this hard-coded 0x00 000000. So just to print off a null pixel to make sure that when we try to print these hex codes, we don't get a seg fault from like not finding a null terminator or getting some other weird undefined behavior. Okay, so once we've printed this off, you're going to see that in the result of calling this function in the terminal. Then right here, what are we doing here? Oh, so right here, we're just capping off with null terminators for safety. So this pixel index is already out of bounds. So we're going to start from where we left off. So pi equals pi. We're going to go up to the maximum pixel index. And then we're just going to fill everything with null terminators, just in case. I mean, because we already zeroed everything out, it's unnecessary, because we have this. But it's better to be safe than sorry, so I don't care that I'm adding some redundancy. Being safe is better than being sorry. And then one more measure to be very careful. We added a extra byte to these arrays, specifically for a null terminator, right? So we're going to take this +1 and add these on to make sure that, make absolutely sure that there is definitely, without a doubt, a null terminator at the end. And the reason for that is because there is the potential that this array, that pi, could have gone all the way up to here when we filled it out. Like, that would be an edge case where it's very rarely going to happen, but every once in a while we might fill up these array to the very last slot. And if we do that, this array is not going to be able to put any null terminators in, and this last resort is the only thing that's going to protect us. So after that, we just print off the original string that was inputted to the function. And what else we got here? Okay, so main is just where we kind of put it all together. So here is the number of arguments on the command line. Here's the argument array. So this is an array of strings. That's why it's a char pointer pointer. If there's not exactly 2 arguments, remember 2 arguments means exactly 1 user-supplied argument. If there's not exactly 2 arguments, then we're going to say the user must supply exactly 1 argument. Otherwise, we'll run the code that we wrote to encode that user argument into our big endian and little endian pixel arrays. Right here, we've taken the result of running our code and just pasted it into the source to get an example of it in action, right? So when we run our source code, we'll see a little tag of my GitHub URL here. And if you search for my GitHub URL in the source code or in the executable, you'll never find it because it's here. So let's give it one more run, and then we're going to be out of here. So let's do a git bash here to open this up. And let's kind of full screen this, make this a lot bigger so you can kind of see this. So we'll do /sp. Oh, it's not sp2 anymore. What the heck do we call it now? And I totally forget what we call this. Okay, well, let's do ls. We are in the wrong folder, are we not? Yeah, we're in the wrong folder. Why are we in the wrong folder here? Pixig. This is not the Pixig folder. Hold on. Full file path to clipboard. That was the first draft. So this is okay. Did we not name this correctly? Hold on. Okay, there we go. Pixig. Okay, here we are. So let's git bash here. So now we're in the correct folder. And let's full screen this. Do /pixig. And then blah, 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 blah. I don't care. But maybe we should say the quick brown fox. It needs to be exactly 1 token. So we can't separate with spaces because it needs to be exactly 1 argument that we're going to encode. And so now we see that the big endian version of the quick brown fox is going to be this. So if we print out this pixel array and reinterpret it as a array of characters, it will print this off properly. And if we try to print this off, well, it depends on what operating system you're on, right? So if you're on Linux, you're going to want to try to print this off. If you're on Windows, then this is the one you're going to use. And then we have an example of this, right? So this is the big endian that doesn't look proper on my Windows system, and then here's the little endian, right? So if you search the source code for this string, you're never going to find it. And even if you open up a hex editor, you're never going to find this. So this is a good way to encode a signature into your source code and kind of hide it somewhere where no one's going to find it unless they know what they're looking for, right? So yeah, that's it. We're done. And hopefully that kind of maybe helps someone. And if you want to see the source code for this, you can go to my GitHub. So let's actually change this URL here so you can see it. So tinyurl.com/getaac, I believe, should be the link. So if you try this, I think that'll work. Let's make absolutely sure that's correct. So if we go to www.tinyurl.com/get-aac, yeah, it will reroute us to my profile. And this is not actually where you want to be. You actually want to be, you actually want to look at my repos, and you want to look at Pixig, right? So prove someone stole your code. Here's how you're going to do it. And I have the video ID in here, so see how it says C video integer ID 0089. If you look in the bottom right-hand corner of this stream, you see that the integer ID is 0089 in the day. Well, the day was Thursday, a few hours ago when I started streaming. But yeah, that's how, if you want to see the video of me actually writing this, that's where we'll go. And let's make a tiny URL for this thing. So let's copy this, and let's go to tinyurl.com, www.tinyurl.com. And let's see if we can, I'm going to guess pixsig is already taken, but let's just try pixsig and see if we can get that. So if you call pixsig, make tiny URL. Oh, look, we're lucky. We got it. So we're going to take this, and I'm going to put this here for you to find it. So if you want to go there, now you have a URL that you can easily type to get to what I have made. So tinyurl.com/pixsig. I'm going to make a note of that in my shortcuts really quick, that is where that is. So pixsig URL, pixsig URL, and pixsig sig URL. Okay, so now we've done a thing. Excellent. So the next thing I want to do, and I'll do it in another stream, is I want to create something to print off the binary representation of a value, because some of the unit test code I'm writing right now needs a way to, I need a way to inspect the actual binary value, a little print off of it, to see what's going wrong with my pixel packing. And I don't know what's going wrong with it while I'm writing my unit test, so that would help kind of solve that. So we're done here. So hopefully that may have been useful, maybe not, but I've done it. So hopefully that was informative, maybe not. I mean, no one really watched this stream, but now I have a stream for this. So prove someone stole your code. So awesome. I am out of here. Good night or whatever, I guess.